Okay, so today is QAOA, and you might know or not know that I already have discussed QAOA both in Circ and in TensorFlow-Quantum, and I even did a weighted QAOA in Circ. But and this is sort of just an improvement on the TensorFlow-Quantum one. It's very similar, but it's more. I guess the goal is to be more explanative in its in its properties, but overall it is very similar. It's just I needed a new version so that I could use it for something else that I'm working on. And so you might be wondering, I do this. It's been kind of infrequently. It's been a while since the variational quantum classifier one, and I have a lot to do now, and also I'm working on some research that all of this will fit into and be used in, and I think that'll be really interesting. So we're building towards something. I did say I intended to do more paper replications, but I think a lot of time that I don't have right now. Hopefully by mid-May, I should be able to be doing that more. So looking at this now, just a quick review of QAOA. The original discussion has plenty of information on that, but we're looking at the max cut problem, which given some graph that you have here, we're trying to make two groups of nodes such that we cut the maximum number of edges. And so you could say the max cut here is 4. We're cutting each of these edges. And so that's sort of the evaluation. So this is a, what's the term? It's a binary optimization problem, because basically, so we have the input, we have QAOA, and then we have a binary output. And this tells us what group each node is in. So there's going to be two groups, right? So if this is node 0, this is node 1, this is node 2, this is node 3. This currently, right, they're all the same group. So this is either 0, 0, 0 or 1, 1, 1, 1. Doesn't really matter. And so, therefore, we can see that we can, understand the cost function that we're trying to minimize, right? We want, for every edge, right, because we have knowledge of the graph, for every edge, we want that edge to be cut, because that means we're increasing the max cut number. And so if we want to increase the number of cut edges, then we want to decrease the number of uncut edges. And so the idea of the cost function, you'll see it in multiple forms, is, for example, with these zeros and ones, it's often written as 1 minus, or I should do it this way. So basically, you can see that if these are both the same number, if these are both 0, hold on, one second. I think I wrote that down wrong, so I'm going to confuse myself. Okay, I did write it down wrong, that's why I confused myself. So we can see here that this is the cost function to be minimized. And this uses the TensorFlow-Quantum notation rather than this notation. So in TensorFlow-Quantum, right, we have the 0 state. That corresponds to the +1 eigenvalue, and the 1 state corresponds to the -1 eigenvalue. So you can either read out zeros and ones when you do this, or you can read out +1s and -1s. And this is done in TensorFlow-Quantum. If you do tfq.layers.sample, this will give you this output. But if you do any sort of expectation value, this will give you this output. So because we're working with expectation values and this update parameter, Using samples in a model is kind of a pain from what I've tried to do. So I just work with the expectation value. So we can see here, right? The cost is minimized when these two are different, right? If these two are different, then this is -1. If these two are the same, then this is 1, right? Because -1 times -1 is 1, 1 times 1 is 1. And so we can see here that minimizing this function will result in maximizing the number of cuts, because we're basically penalizing for not cutting an edge. And so that's sort of the key idea. Maybe I'll just quickly review the structure of QAOA. QAOA is made up of input of superposition. First, we go into it and we have Hadamard gates here. And then we have alternating cost and mixer layers for this Hamiltonian. The cost Hamiltonian to mixer Hamiltonian. The cost embeds the problem. And so this will change, and oftentimes this might, but the cost Hamiltonian will change depending on what problem you're working with. So I'm just using a max cut one. I don't even know what the other ones are. Just binary optimization isn't something I'm an expert on. And so, but you can look, actually, I know Penny Lane has a bunch of different examples of the problem sets. There's like maximum independence set, stuff like that. And so, and then the mixer is just sort of increasing the almost expressivity of the model, right? Because if you just do a single version of this, you're going to get some eigenvalue of this operation. And so the mixer just enables more diversity and function representation, basically, is how I interpret it, at least. And so this is done each edge. So for the cost Hamiltonian, in this case, each edge gets converted to this format where this is the two, this is edge part 1, this is edge part 2, and then the mixers are just RXs on every qubit. And so, yeah, there's more information in the original. I'm going to cross-link these together, hopefully. So, yeah. Now let's get into the code a little bit. There we go. So we have the usual imports, TensorFlow, Tensorflow-Quantum, Circ, all this stuff. Network X is how we make graphs. This converts to a decimal. So first we consider just a 10 node graph. And so this is the number of qubits that you're going to have. It scales linearly, right? 10 nodes, 10 qubits. The regularity is how many other nodes each node is connected to. So this is a regular graph, which means that every node is connected to the same number of other nodes. You could do Network X also makes it easy to do like Erdős-Renyi graphs or something where it's like probabilistic connections. So now we can see we define a mixing Hamiltonian layer. So we take in the circuit, the qubits, and the one parameter. So each Hamiltonian has exactly one parameter. So we see that, okay, for each qubit, we do an Rx of 2 times that parameter. That's just how it gets converted. I'm pretty sure you could do exactly the same function without the times 2. But this is the conversion that you have. And so it's simple, Rx of every single qubit. The cost Hamiltonian is as I described before. We take in the graph, the circuit, the qubits, and the parameter. We do the C0 from controlled by the first edge point to the second edge point. We do RZ on the second edge qubit, and we do another C0. And so that's one layer of the cost Hamiltonian. So then we create the qubits, so however many nodes we have. We initialize the circuit. And this P is just referred to as the depth. I don't know why it's called P, actually. I don't remember, but that's just the depth of the circuit. And so the number of parameters, therefore, is 2 times P because there's 2 Hamiltonians in every layer, and therefore Since every Hamiltonian is one parameter, there's 2 times p parameters. So we create the parameters, and then we create the circuit by alternating these cost and mixer Hamiltonians. And then we initialize the input. So as I said before, the input is the Hadamard, so an equal superposition of all states, which is done by applying a Hadamard gate to every single qubit. And then we convert that to a tensor. And this is the cost, right? So for each edge, we do a polystring. I don't actually know, now that I'm thinking about it, I don't know if this polystring is actually necessary. Because this takes as input gates, but it's just good practice, right? To know this sort of declares what data type it is. And so a polystring is just a string of poly operations, right? So z's are poly operations. So we can see this is exactly the cost function for each edge. The cost is 1/2 times the expectation value of each qubit, or the z measurement. So we create the cost, then we have our standard TFQ model setup, we have the string input, we have the parametrized quantum layer with the QAOA circuit created from these alternating Hamiltonians. This cost, I should not call it test anymore. That's when I didn't know if it would work. And then we have an adjoint differentiator, and this is just speed, right? I don't want to sit here and wait 10 minutes, even though it's not that long for something to converge, just because it's easier. So yeah, that's just why I use it. And also now that I've been using Windows subsystem for Linux more, it's a lot easier. We create the model and we use Atom as the optimizer. And then we go through, we keep track of the losses. This is what epochs is on. We create a tolerance so that it's when it's sufficiently converged to a solution, we're good. And we just initialize the old error. And so I just want to say one thing before we get into this, that these losses are not actually impactful. They don't mean like a lot, right? You can't say, oh, the loss is -1. That means it's getting it, 20% right or something. It's harder to interpret this loss because we don't know what the perfect, well, we can figure it out, but when we're training, we don't know what the perfect solution is. So it can be hard to interpret these losses. So we get the output of this QAOA, which is just the error. We apply the gradients, calculate and apply them. We convert it to numpy so it's easy to print. And then we keep track of it. We print the epoch into error. And then if the difference, right, between the old one and the new one, so basically if these updated parameters aren't sufficiently improving on the old ones, then we just stop, right? That's when we've said, okay, we finished our optimization, we're done. And then we plot this, and then here we can see this is exactly the same from the old code. We can see that this samples, here we can see the sample function. So we sample it 1,000 times. We and convert this to the bit strings, and then we generate all cuts possible to find the max cut, and then we get basically the accuracy of the quantum cut. And so now we can just run it basically. Let's get this, okay. Oh, now I gotta go over there. So we're gonna do Python QAOA. And this is a 10. Oh, maybe I should zoom in a little bit. I always forget to do that. Yeah, that's much better. So this is a 10 qubit setup, 5 layers. So here we can see the epoch, and that converged pretty quickly, right? You can see not great accuracy here. Let me see if I can bring up. Can I add this? Let me see. Ooh, that's not what I meant to do. Let me do window capture. There we go. So you can see this is just plotting the loss function. So yeah, that wasn't the optimal strategy. You can see points, 70% isn't great. So let's try, I'm just going to try another example. We'll try a 8 node graph, 4 regularity and depth 4. And we'll just try it, right? This is one of those things where you just got to try things. And so now we'll see this. I kind of wanted one that would take a little longer to update. You can see it's converging pretty quickly here. And these are the parameters, right? But you can see this one has a lot better accuracy. And is what this is essentially saying. So now let's consider a big one. I'm going to do 14 nodes, regularity 6, and depth 8. So this one might take a little longer because this is a big old circuit, right? There's not a ton of parameters, but it's pretty sizable. Yeah, so you can see it takes a little while to do this, and this is with the adjoint differentiator. So even with this takes a second. And so yeah, as the graphs get bigger, optimization can get harder and the solutions can be harder to find. But in general, increasing the depth can help with the solutions. So I might pause here and just let it run, I guess, since it's still decreasing. Okay, here we can see the loss function. You can see it took over 400 epochs. So now I can get rid of that. And you can see the final accuracy about 0.8, which is decent for a graph that big, but there's a lot of different techniques to optimize QAOA, and there's a lot of advancements. But that's sort of just the general idea. Once again, the code will be available and linked, and I'll cross-link the other video I already made on this, and in that video I'll also link this one. But this is just an updated, easier to use, and I think overall better implementation. So yeah.